So today I'm going to talk about genome assembly and variant calling, and I'm going to be doing that mostly from the perspective of algorithmic improvements, although our apps team are giving a presentation about some of these algorithms and the brand new science that we can do with them in the main session in the next talk. So definitely go and check that out for more on this kind of information. So, when we're doing sequencing, the fundamental question that we're trying to answer is what is the genome of this sample in front of me? But there's lots of different contexts in which we could be asking that question. Sometimes we want to do this completely from the data that we're gathering from the device, so there's no reference sequence. Obviously, that would be the case if we've got a new species. It might also be that we don't want to introduce a reference to bias our analysis towards one specific existing artifact, but rather have a completely de novo approach to this. So in that case, we need to give our base-called reads to an assembly algorithm. If you've worked on assembly, you'll know this is a notoriously difficult computational problem, and we find that errors are often introduced in this process. Now clearly this is not ideal, we'd like to remove them, so we often have this secondary step which we call assembly polishing. And what we're doing there is we're taking the reads that we use to produce the, sorry I'm skipping ahead here. Yeah, we're using the reads that we use to produce that draft assembly, aligning them to it, and then we give that data to a neural network, which we call the assembly polishing model. And the job of that polishing model is to go through that draft assembly, find any assembly errors, and correct them using evidence from the reads that are aligned to the different locations. So that's the case where we don't have a species reference, but what about if we already have a high-quality reference that we want to use? Well, in this case, the task becomes, how does this individual differ from the species reference? And we can skip the assembly process entirely, so we instead align the reads to that reference, as you can see on this slide, and give that to another neural network, in this case a variant caller, which will output a VCF file to hopefully answer our question. Hopefully you can see from this slide that the input data to both the assembly polishing model and the variant calling model are very similar. And we believe it goes actually a lot deeper than this, and that fundamentally these two models are trying to solve the same problem. So that's a little spoiler for what I'm going to talk about later. But for now, let's focus on this first box, which is assembly. So it was 3 years ago that the scientific community finally completed the human genome. And this was thanks to a heroic effort thanks to the T2T consortium. It involved researchers from across the world, multiple different institutes, lots of different sequencing technologies, and a significant amount of manual intervention. But obviously this was a landmark achievement at the time, and I'm sure you've all seen the front cover of Science and various other journals lauding this amazing achievement. It's a sign of how quickly the technology's moved that we are now at a point where we can get complete T2T assemblies using just Oxford Nanopore data. And my colleague Sean demonstrated this at London Calling last year. At the time, this assembly that Sean showed was possible thanks to firstly improved base calling accuracy, but also our ultra-long read kit and deep learning-based read error correction algorithms such as Hero. This year, we've seen another huge step forward in terms of genome assembly. And we're now moving to a point where we can get near T2T quality assemblies using just standard LSK simplex data. A big part of this is this new assembly algorithm, HiFi-ASM-ONT. So this has been developed by Haiyue Cheng, who's an assistant professor at Yale. And what Haiyue's done is tweaked his existing assembler to better work with the read length and error profile that we would see in LSK simplex reads. I remember when I first ran this on some sample data I had, it was one of those times where you look at the results and you think, that's not right, that's far too good. And I've learned from bitter experience that 9 times out of 10, that's because I've done something silly and my colleague's going to laugh at me fairly soon. But actually, this was one of those 1 in 10 times which really invited me to reconsider what's possible with this data. So to put some numbers behind that, from a 50x dataset of human reads, we can get 23 chromosomes assembled completely without gaps, 10 more chromosomes scaffolded, and for this assembly, which is from the preprint, the N50s were over 130 megabases. So that's really coming up to what we were getting before using ultralong and Hero, with the added benefit that this is incredibly fast because we don't have that deep learning-based read error correction step. We're already getting fantastic feedback on this from the community, who are using it to assemble both human and non-human samples, and you can see a quote from Alan Scott from Johns Hopkins University, who's been using it to assemble snake genomes on the bottom right-hand corner of this slide. And Haiyue gave a talk in the bioinformatics section about this earlier. So if you wanted to hear more about the algorithms and also a few more results, I'd recommend having a look at that on catch-up. Okay, so our assemblies are getting more contiguous than ever before. But what about the other axis of assembly quality, which is their accuracy? Well, this is something that we've also had some progress on recently. It's helped by improved base cooling, of course, but we've also found a new architecture for that assembly polishing model. So these are our read-level feature polishing models, and the main difference between this architecture and the previous architecture is the type of information about each read that they get access to. So the previous models would just look at the base cools and strand direction for each read when it's trying to polish the assembly. These new models have access to a much broader range of information about each read. So they're looking at things, for example, like the quality score, which is a reflection of how confident the base cooler is in the sequence it predicted for each read. The alignment quality, so has this read aligned to the correct part in the draft assembly, and even optionally some signal level information in the form of dwell times. What this means is that the model can make a better decision between what is an assembly error versus what's a error in this individual read. I first spoke about these models at NCM a couple of months ago when they were still in development. I'm pleased to say that they're now available for customers through the new Dorado polish command, and we have read-level feature polishing models for both V5 and V5.2 for both the hack and SUP base coolers. Just to give you a feel for the fact that these goes hand in hand with those improvements that we saw with Hi-Fi as ONT earlier, we took one of those one of the assemblies from that preprint, and we tried polishing it with our latest models. And what we notice is that we get a significant improvement in accuracy. So you can measure the accuracy of these assemblies by aligning them to the Q100 T2T reference. And what we find is that after polishing, the assembly aligns with an extra 2.5 Q points for both hack and SUP. So that means almost half as many errors in the polished assembly as there was in the unpolished assembly before. Okay, so that's all I'm going to talk about on the subject of genome assembly, but what about variant cooling? Well, as Chris said, it's long been our goal to make Dorado more than just a base cooler, but also a complete and performant platform for secondary analysis. We've already got Dorado correct. I just spoke about Dorado Polish, which implements assembly polishing. Today we're taking the next step in that journey, and we're giving Dorado its very own variant cooler. This is available in Dorado from yesterday. So if you download Dorado, you can run this model. We're only making one model available initially because this is a preview release. So we're releasing a V5 hack base cooler model. We think that lots of people will have some data that they can try this out with though. And as with the rest of Dorado, we want this to be as easy to use as possible. So that means sensible defaults and multi-GPU acceleration. And you can really see, hopefully, how simple this is to get a VCF from your BAM by a full command on the right-hand side. So you just give it a BAM with the reads aligned to a reference, and Dorado should handle everything else. I want to emphasize that this is more than just a port of an existing variant calling algorithm, but rather a completely new way of approaching this problem. It's something we've been working on for the last couple of months. We've got lots of new ideas that we're very excited about. To give you a quick spoiler, it's essentially a tweaked version of those read-level polishing models that we saw before. There's too much technical detail to go into in this presentation, but we're going to make a preprint available with the full details of the algorithm soon, once we've ironed out some of the remaining wrinkles. So, how good is it? Well, as I said, this is still a preview release. We've still got things we know we can improve, but what we've seen so far is really encouraging. So for the model that we're releasing in Dorado V1 today, we're achieving state-of-the-art indel F1 on the popular whole genome in a bottle benchmark, and we're noticing particular improvements in long homopolymers. So you can see there's a 4% boost in indel F1 score on all regions, with approximately the same performance in coding regions where there's less of those long homopolymers, and also about the same performance as in SNPs compared to Claire 3, which is our existing recommended variant cooler. This is really the start of Dorado variants journey, and we've got lots to work on. We'll carry on getting performance improvements, both in terms of speed and accuracy, as well as offering models for the new V5.2 base coolers. And as I said, that technical preprint is coming. Otherwise, we want to carry on supporting customer workflows, so we'll carry on making Claire 3 models available in the near future until Dorado variant is integrated as well as integrating those read-level featuring polishing models that I talked about a little bit earlier. So that's all I've got today, but I'm looking forward to hearing your questions later, and otherwise, thank you for your time.